Hello, Math 3. Welcome to Lesson 7.3 in our statistics unit. Today's topic is the normal distribution. So, what makes a normal distribution? What's it all about? Well, it's called the normal distribution because it happens so frequently, especially in nature. So if you start thinking about anything in nature, for example, measuring the height of plants or animals, weighing things that occur in nature, you're going to find that there's a few that are really tall, there's a few that are really short, there's a few that are really heavy, there's a few that are really light, but most are kind of in the middle. So a normal distribution is a distribution where you have a lot of data in the middle, and then as you move further and further from the middle, it's less and less common to observe data there. So something like this one is approximately normal. Okay. A distribution like the top left, this is called right skewed. The bottom left, this one is called left skewed. And this distribution over here is approximately uniform. Okay. So that one we'll say is uniform. We'll say this is left skewed. And this up here is right skewed. And this is approximately normal. Okay. It's not just in nature. If you think about things like the SAT or the ACT, many tests will be normally distributed, where a lot of people get around the average, and then there's a couple people that are really, really, really good and get really high scores, and then there's a few people on the other end that get really low scores. So lots of things are normal, and that's why we call it normal, because it is actually normal to have that distribution, because it's, again, so common. All right, so let's just kind of write a few facts that'll help us identify normal distributions. So, number one, normal distributions are symmetric. And they're not just symmetric in any old way, they're symmetric around the mean, right? The mean will be in the middle, and then the two sides will match up. Okay. And since they're symmetric around the mean, and the mean's in the middle at the high spot, that means the mean and median, as well as the mode, are all equal right in the middle. So the mean, median, and mode are all equal. That's in a perfectly normal distribution, right? This one up here, you can see it's approximately normal. It has this kind of little bump there in the middle. So on that distribution, they're not all equal, but they're close. They're approximately equal because it's approximately normal. Okay, the third thing we can say is the area under the normal curve is exactly 1. Or in other words, it contains exactly 100% of the data from the distribution, which kind of makes sense. It wouldn't make sense to draw a graph that doesn't contain all of your data. So that's all we're seeing there. It contains all the data when we draw the graph. Okay, now let's talk kind of about the general shape. Normal distributions they're high in the middle and low on the ends. So you could write that, high in the middle, low on the ends, or you could say they are more dense in the center and less dense in the tails. Okay. In other words, another way to describe this more succinctly, people say they are bell-shaped. You may have even heard people say, oh, a bell curve. A bell curve is just kind of a way of describing the shape of the normal distribution. It looks like a bell. Okay, normal distributions. The way we can tell them apart, one normal distribution from another, because they're not all the same, right? If I say heights of trees versus heights of humans, both are normally distributed, but trees tend to be quite a bit taller, right? So the way I can define a normal distribution and tell one from another is by looking at two key parameters. So they're defined by two parameters. Okay, those parameters are the mean and the standard deviation, two things that we already learned this chapter. And here is kind of the shortcut. We would write capital N, that tells somebody, oh, we're talking about a normal distribution. Then we would give an ordered pair where we would list the mean and the standard deviation. I don't think I went over this symbol here. This is called mu. That's another Greek letter. Mu is the mean of the population. We talked about x bar previously. X bar is the sample mean. So x bar is used to approximate the actual parameter mu. Okay, so this is if we had all of the data, a census, right? Then we would have mu. And that's how we would define the normal distribution, because the normal distribution is based on all of the data. So anyway, that's how I can define and differentiate one normal distribution from another, list its mean and its standard deviation. All right, now to the most important things. We know for all normal distributions that approximately 68% of the area or data, whichever one you want to say, area or data, right, is within one standard deviation of the mean. Oops, went off the screen there. Sorry about that. Of the mean. Okay. And that's for all normal distributions. Again, approximately. Not exactly, approximately. All right, and then the last fact, approximately 95% of the area or data, I'm short on space, so this time I'll just say area. No, I have space down here, or data. Right, same thing. Because the area would be, all the area is 100% of the data, right? Because it's a histogram of the data set. So the area or data is within 2 standard deviations. Of the mean. Okay, so those two things are the most important things to remember. 68% of the data will be within 1 standard deviation of the mean. Fold that up. 95% of the data will be within 2 standard deviations of the mean. Approximately. Okay? So we're going to use that information to answer some questions about probabilities. Okay, so here we've drawn a nice normal distribution. Okay. So in the center is the mean, the perfect theoretical mean, because we've made a perfectly nice normal curve. Okay. Now, as I move away from the mean, I get less and less frequent occurrences of data. Okay, so I can go 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. I could keep going, but once I've gone 3 standard deviations below, there's not a whole lot of data left. So that pretty much is far enough. And same thing on the right. Okay, I can increase, and once I hit 3 standard deviations above the mean, there's not much data left. All right, so we said 68% of the data will be within 1 standard deviation of the mean. So in other words, about 34% of the data will land here, and about 34% will land there, right? 68 total within 1 standard deviation. Okay, so that's the 68% right there. All right, now if I go 2 standard deviations, so from here to here, right? Notice I'm capturing more of the data. I'm going to capture about 95% of the data if I go from here all the way to here on the distribution. So doing a little bit of arithmetic, if I say 95% minus 68, I would then have these 2 unknown amounts, divide that by 2, and I would find out that this is about 13.5%, and this is also about 13.5%. You see, because it's symmetric about the mean, these 2 sides have to match exactly. Okay. Continuing on, we didn't say this on the previous page, but if we go 3 standard deviations, we've captured 99.7% of our data. So over here would be about 2.35% and 2.35%. And that leaves just this little bit left, right? 0.15% over here and 0.15% over here. The really rare occurrences, really far from average. Okay. Oh, one side note. This point right here, okay, and right here, these, when you sketch your normal curve, these will land on a change in concavity. So here you can see my graph is bending up. Now it's still technically going up, but it's no longer bending up. At this point, it starts actually bending downward, right? If you had a, think about if you have something straight and you're trying to match this curve, right? Over here on the left, I have to push this up and bend it up. But once I hit this point here, I now would say, oh, to fix this, to match it, I would have to push it down over here. So that's called concave down. It's bending down. Okay, and that's how you can find visually where 1 standard deviation will land. It will always land at a change in concavity on your graph, okay, where it changes from bending up to bending down. Just a side note, you'll learn a lot more about that in calculus. Okay, so let's try some problems now that we have this information. So it's given that we have a normal distribution, okay. Normal, so I'll go like this. Mean is 27. Standard deviation is 5. See, I've just taken all of those words and with those symbols said the same thing. Nice shortcut. Okay, it asks me to sketch this curve, so I'll just go ahead and draw this in. Not perfect, but good enough. And the mean, 27, 1 standard deviation. So adding 1 standard deviation would take me to 32, right? 27 plus 5. Subtracting a standard deviation would take me down to 22. Okay, adding another one, 37. Over here, subtracting another one, 17. And if I go one more, this way I'll be at 42, and this way I would be at 12. Okay. All right, if you want, you can copy all of these percentages in here, if that helps you. But you don't have to. You can just kind of refer to these percentages. All right, so first question. Find the probability, if I randomly select a piece of data, that it lands between 22 and 32. So it lands between these two. Well, hey, that's the 68%. That's within one standard deviation, approximately 68%. Okay. All right, next question. What's the probability that if I randomly select a piece of data, I get a data point between 12 and 27? So from here to here. Okay, well, I could add up, right, this plus this plus this, or I could kind of go at it in a different way and say, hey, from here all the way over is 50%, and then just cut off that last little bit. So there's always more than one way to get there. So you could say 50% minus the 0.15, or you could say 2.35 plus 13.5 plus 34%. Either way, you'll get the same answer, 49.85%. Again, we're technically being approximate here, even though that's an awfully accurate number. Okay, that would be the value if we had a perfectly normal distribution, right? If we're approximately normal, we're approximately that. Okay, on to the next one. How about if I'm between 17 and 37? So that's from here, 17, to there, 37. Well, that looks to me like it is 2 standard deviations, right? So that's 95% approximately. Okay, next, I'm out of colors. Go back to red. So at least 22, that means 22 or more. So the simple way to do that is, well, from here over is 50%, and then I've got another 34% right there. So I would say 50%, right, the upper half, plus the 34%. So that would give me 84%. Okay. All right, next, at least 37. So at least 37, that's from here over. Okay. Again, there's more than one way to do it. I could just add up these two numbers, or I could do 100% minus all of those. There's always lots of ideas on how you could do it. The way I'm going to do it is I'm going to say, well, this is 2 standard deviations. And if I go to the right, I've just got these 2 bits to add together. That seems fast to me. So that's 2.5%. All right, my last question on this distribution. At most 32. So that means 32 or less. Okay, so I'm going to say, hey, there's 50% and then another 34%. That's 84%. And there you go. That's how we use what we call the empirical rule to answer these questions. The empirical rule is 68% of the data within 1 standard deviation, 95% of the data within 2, 99.7% of the data within 3. Okay, so let's try a few more problems. All right, college only accepts students who are in the top 16%, blah, 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 normally distributed. Mean is 25. Standard deviation is 3.8. What is the least score you could earn and be accepted? Okay, well, I can draw this if it helps me. There's my mean. Okay, if I go 1 standard deviation above, I would be at 28.8. And now look, that would be 50% plus 34%, right? So that would be 84%, which means this area over here, that's the top 16%. So I need a score of 28.8. Okay. Now, of course, usually you can't get a score of 28.8, so that's why it says nearest whole number. So I'm going to say a score of 29. Okay, moving on. Okay, blah, 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 blah. Mean is 12, blah, blah, blah. Standard deviation 2.8 and normal. So, same thing. I'm going to replace all those words with these nice convenient symbols. Mean of 12, standard deviation 2.8. And I can draw the normal curve. Okay. And now this time we're saying, oh, we want the middle 68%. So that means 1 standard deviation above and 1 standard deviation below. So from 9.2 to 14.8, it does say approximately. So I'm going to round those off and say between approximately 9 and 15 bottles of soda. Okay, oops, can't quite see it. All right, and if you said between 9.2 and 14.8 bottles of soda, I would not mark you wrong. That's perfectly fine. All right, moving on. Okay, as I mentioned earlier, SAT, ACT scores are normally distributed. A lot of people get kind of average scores, and then a few people get really high and a few people get really low. So here we go. The ACT back in 2010 had a mean of 21 and a standard deviation of 5.2, and it was normally distributed. Okay, so I can take all of those words and abbreviate with that. Okay, so let's try to sketch the curve. Okay, my mean 21, go 1 standard deviation. So that's 26.2. Go another standard deviation, 31.4. Okay, and then in the direction you don't want to go when you take the ACT, 1 standard deviation below, 15.8, and another standard deviation below, 10.6. Okay, what percent of the students scored below 21? Well, 21 is the mean, so half. About what percentage of students scored below 16? Okay, well, 16 is about here, so we're saying from here over, hopefully you remember that would be 13.5% right there, and then this whole bit would be 2.5%, right? If I just keep going. So about 16%. Okay. Let's see, about what percentage of students scored between 11 and 26? Okay. Well, again, I don't have 11, I have 10.6, but that's approximately there, right? We'll say that's approximately 11, and then that's approximately 26. So we're saying between here and here. Okay, well, that's 34, that's 34%, and then we have this 13.5. So add those three together, and we'll say it's about 81.5%. Okay, next question. What score would put someone in the 97.5th percentile? Okay, so 97.5% of test takers scored below that. Well, remember this is, I'll do another color. This is 13.5 here, right? So if I add all of that up, right, there's 50%, 84, 97.5. So right there gets me to the 97.5th percentile. So that is a score of 31.4, which we can't really get that, so we'll have to round that to up to a 32. Okay. Hopefully you see why I rounded up, right? If I went down, I would be moving to the point where I'm no longer making the 97.5th percentile. I'd be a little under, right? I'd be like the 96 point something percentile maybe. So if I want to be sure that I've made at least that cutoff, right? This is kind of inferring a greater than or equal to. So greater than or equal to 31.4. I'm going to have to get 32. Okay, next question. What if you got all the data for all the test takers? That would take a lot of time and be very expensive. So instead of getting all the data, what if you just did a random representative sample would you get a mean of exactly 21 in your sample? Maybe, but probably not. You'd probably be about 21, approximately 21. So what do I think the mean would be? I think it would be about 21 from my sample, assuming I used a nice random sample method that got me good unbiased data. Okay. How confident am I? Well, it depends on how large my sample is and how good of a job I did at getting a representative sample. So I will write that. It depends on the sample size and the sample method. Both are very important to get good representative data. Right? Realize if my sample size is one person, I'm probably not going to get 21. Very, very unlikely, right? If my sample size is 100 and it's a nice random sample, the mean of those 100 students is probably going to be pretty close to 21, right? So larger sample means I'll be more likely to be on target. Okay, next question. You got a friend? Congratulations. Your friend's applying to a college, and this college only takes the top 1%. Okay, Calvin scored 33 on the ACT. Does that put him in the top 1%? Okay, we're going to investigate this more in the next lesson. Notice, if I go one more standard deviation over here, right? I was at a score of 31.4. If I go one more standard deviation, I'm now at a 36.6. I'm actually, if you know anything about the ACT, I'm actually off the table, right? ACT only goes to 36. But that's my problem. I want to be in the top 1%. This is in the top 2.5%, right? So somewhere in here is the top 1%. We're going to learn how to find that next lesson exactly. So at this point, the best I can do is say, he's in the ballpark, right? He's right on that edge if he made the top 1% or not. So we'll say he is right on the edge of being admitted. He's right in that kind of 1% ballpark. Okay. Next lesson, we'll have a way to test exactly where he landed, what percentage. Okay, on to the last page. This is something we do a lot in AP statistics. We actually have the raw data, and we have to ask, well, did this data come from a normal distribution or not? So what we do, first thing, is graph it. So let's go ahead and make a frequency histogram of this data set and see what its shape looks like. Okay, so I'm going to start with my first class interval from 550 to 600. So there. Oh, I got to stop. So it looks like I had 4 pieces of data in that class interval. All right, my next class interval, I'm going to go from 600 to 650. So these weren't in order, but it worked out okay. That is a total of 10 pieces of data. Okay. My next class interval is from 650 to 700. Okay, so counting that up, I've got 15 pieces of data there. And then going from 700 to 750, got 5 pieces of data there. And then from 750 to 800, 3 pieces of data. Okay. So, does this graph look like a normal distribution? So what you ask yourself, is it high in the middle? Yes. Is it low on the tails? Yes. So is it perfectly normal? Well, no, but we don't have enough data to necessarily make it perfectly normal. To make it perfectly normal, we would need a lot of data. There is, again, always some variation when we take samples. And in this case, I'm going to hypothesize that the actual data, if I got every single person's info, would be pretty darn normal. And then this sample came out just a little bit off, but it's approximately normal. Okay, so that's what I'm going to say. It's approximately normal. And why? Well, because it is high in the middle and low on the ends. Okay, you can talk about center and tails, or you can just be real simple like that. Good enough. All right, last set here. The heights of men, blah, blah, blah. Normally, mean, standard deviation. So right there, I'm going to say normal 70, 3. And now all of that information is contained right there, 73. Okay. All right, if a person is chosen randomly, what's the probability he is more than 76 inches tall? Well, let's kind of draw a little normal curve over here. There's 70. One standard deviation would be 73, and 2 standard deviations would be 76. So what's the probability is more than 76? That's this tail over here. That's a pretty small area, right? That's the 2.5% of the data lands over there. Okay, because I'm 2 standard deviations above. All right, what percentage of the group is between 61 and 67? Okay, so I got to go down here. Here's 67, 64, 61, way over there on the edge, right? So again, going back to our empirical rule and adding up each piece that fits the question, right? This would be from here to here is 2.35, and from here to here is 13.5. So 2.35% plus 13.5%, which is 15.85% chance. Okay. All right, last question. You own a onesie company, blah, 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 blah. What percent of the men would be able to wear your onesie? So we're looking 3 inches above or below 70, right? So we're saying from 67 to 73. What percent will that capture? Well, that's the middle 68%. Empirical rule. There we go. All right. Enjoy your homework. I hope you like statistics.